Hi there. For this video, we'll be discussing about the complex conjugate root theorem. So let's write that one down. Complex conjugate root theorem. So in this study, we'll be dealing with irrational roots and complex roots, and although this is not part of the scope of a traditional study on polynomial equations, since in polynomial equations we usually just deal with real numbers, for this one, this theorem will be useful in creating a polynomial equation given a roots that includes a complex root or a radical or irrational root. So it goes by, if we have a polynomial equation and a plus bi is a root of that polynomial equation, then it immediately follows that a minus bi is also a root of that specific equation. And similarly, it goes vice versa. If a minus bi is a root of that equation, it follows that a plus bi is a root of that equation. So examples of this are, if we have 2 plus 3i, it follows that 2 minus 3i is also a root. If, say, 5 minus I is a root, it follows that 5 plus I is a root. The idea of conjugate is very broad, and it requires more study, but essentially it's just the change of signs. For now, that's how we will be viewing conjugates. Aside from that, we can also apply this to radicals. Although radicals are not part or are not treated as complex numbers, we can treat it is an irrational number, but in this sense we'll treat it as a complex in this field, since when we have square root of, say, x, it immediately follows that negative square root of x is also a root. So as you can see, the change of signs out here, from positive out here to negative. And the reverse follows as well. So if we have a root of 5 plus square root of 11, it follows that 5 minus square root of 11 is also a root. If we have square root of 17, it follows that square root of 17 is also a root of that equation. So to understand this more, let's have this example. If we are provided that the roots of an equation, a polynomial equation, are negative 2, 1, and 2 minus 3i, and we're provided that the degree of that specific equation is of degree 4, our goal is to find that polynomial equation. As you can see, we have 3 roots out here, and we have a degree 4, so we know that there are at most 4 roots for this polynomial equation. To determine the 4th root, we can't just put any number out here. We can't choose negative 1 or 3, since we have a complex number out here. So by the complex conjugate root theorem, it follows that the last root out here must be 2 plus 3i, since they are like partners. If one is a root, the conjugate is also a root. So with that, we now have this. So x, if negative 2 is a root, we can write it as x equals negative 2. Then we move the negative 2 out here, and we'll have here x plus 2. Then for 1, we have here x equals 1. Move the 1 out here, and we'll have here x minus 1. For this 2, we can write this as x equals 2 minus 3i. Then moving this 2 to the left side, we'll obtain x minus 2 plus 3i. And for this one, we have x equals 2 plus 3i. Move both to the left side, and we obtain x minus 2 minus 3i equals 0. So this is already our polynomial equation. But again, since we have complex roots out here, we'll treat this polynomial equation in the complex field. So we can end here, but we can also simplify this further. So first, we multiply this 2. So how do we multiply polynomials? The general method is we multiply each term to each term, the other polynomial. And so with this, multiply it to each, and so on. So we'll have here x squared, then x times negative 2. That will give us negative 2x. X times negative 3i, that will give us negative 3ix. Then next, negative 2 times x, that will give us negative 2x. Negative 2 times negative 2, that is positive 4. Negative 2 times negative 3i, that will give us plus 6i. Lastly, 3i times x, that will be positive 3ix. 3i times negative 2, that is negative 6i, and 3i times negative 3i, that is positive 9i squared. And from here, observe that we have negative 3ix and positive 3ix, so that cancels out. We also have 6i and negative 6i. Then, note that 9i squared, this one is equal to negative 9, since i squared is equal to negative 1 by our knowledge on complex numbers. So simplifying this will simply be x squared. This we have 2 negative 2x, so that's negative 4x, and 4 minus 9. Oops. A correction, this should be negative, since we have 3i times negative 3i. This is negative I squared, which will result to 9. And so 4 plus 9 will be 30. So we can replace this whole expression out here as x squared minus 4x plus 13. Now, by multiplication process, we can further simplify this by multiplying each one of this. But I'll leave that to you as an exercise. And you can verify that multiplying all these would result to x raised to 4 minus 3x cubed plus 7x squared plus 21x minus 26 equals 0. If you don't know how to multiply polynomials, you may check out my multiplication of polynomials the general way. Let's have this next example. If we have the roots to be negative square root of 3 and 5, and we are tasked to find a degree 3 of a polynomial equation, how do we solve this one? Again, by the complex conjugate root theorem, we know that since we have a radical out here, its partner must also be here, which is square root of 3. And now we have 3 roots, which matches our degree of 3. So we can now find the polynomial equation. So in here, you can write this as x equals negative square root of 3. Move this to the left side. To obtain x plus square root of 3. Then we do the same process for the remaining roots. So for 5, we'll have x minus 5. For square root of 3, we'll have x minus square root of 3 equals 0. Now to simplify this, we can first multiply x plus square root of 3 and x minus square root of 3, since this is a sum and difference. So its outcome will simply be square of the first term minus the square of the second term, which is 3, times x minus 5 equals 0. Now we can apply FOIL method. So we have first, so that will be x cubed, the outer, so that's x squared and negative 5, that will be negative 5x squared, the inner terms, which is negative 3 and x, so that will be negative 3x, and lastly we have the last terms, which is negative 3 and negative 5, so that will be positive 50 equals 0. And we are done. We have found a polynomial equation of degree 3 that contains the given roots plus this by complex conjugate root theorem. And so that is how we apply the complex conjugate root theorem. It's very helpful in finding the polynomial equation given the roots that involves complex and radicals. To end this, here's an exercise that you can work on. Suppose that you are given the roots negative 1, square root of 2, and negative 3i. And your goal is to find a polynomial equation of degree 5. So as a hint, you'll apply the theorem twice. apply theorem twice. Why? Since we have a radical out here and a complex number out here. So you'll apply the complex conjugate theorem on those two to obtain the 5 roots for the degree 5 polynomial equation. So that's it for this video. I hope you enjoyed this one, and feel free to comment down below your answers and solutions to these exercises and the one that I mentioned in the first example. So that's it, and that's all for this video.